think we should start. So, welcome back. I hope everyone of you has enjoyed one for Thanksgiving. So, because in the last lecture there are only like 5 students showing up in the last lecture, I guess most probably because of Thanksgiving. And unfortunately, our do you have a question? Okay. So, our camera. The device from department, the camera is broken. So the last lecture's video and today's video will be recorded by our TA's laptop. So after that, but there is no streaming function. So after the lecture, the video will be uploaded to the YouTube, but it's not in a UFU like data channel. And our TA will just share the link of the video in cameras. So hopefully every one of you, if you need, just click into the link and watch the video in the YouTube. And that's one thing. And the second thing is that after this class, and the TA will release the 5th homework, the last homework. And the deadline will be next Friday, before midnight. Next Friday, which this time the time for you to finish the homework is a little shorter than previous ones because we want to allocate some time for you to prepare your finals. You have a final exams. You have a one-on-one final exams, right? And also some of you might have to prepare for the final projects and final reports and etc. So please start as early as possible. And third thing is that next Monday will be our last quiz, the 4th quiz. So again, it will span about 30 minutes, and you can now use laptop and calculators, but you can just start to review what you have discussed after the last quiz. And the next Wednesday, our schedule is as follows, because next Wednesday will be our last lecture. And before next Wednesday, we'll release one practice paper, which is harder than the final exam. So we'll release the practice paper at the end of this week. So we hope you can do it by yourself before next Wednesday, because next Wednesday, our TA will discuss the solutions of the practice. Of course, we'll release all the answers of the quizzes. We'll release in the cameras, and we'll also discuss solutions of few typical problems. Well, a lot of students make mistakes on that, and to help you review the course. So this the final step I want to mention is that from today, we'll have the course evaluation. Maybe you have already received the email. I think I'll highly encourage you to fill the course evaluation because it's really beneficial for us to improve the class and also help like your fellow students or juniors who are planning to register this class next fall. So later, the TA will create an extra assignment, but it's totally optional. And to finish the assignment, you need to submit confirmation, a screenshot. If you really do the course evaluation, just submit a screenshot showing that you have filled the course evaluation form, and then you will earn the 5 reward points. That will, if you can finish it before the final exam, the 5 rewarding points will be automatically added to your final exam, your final grade. But you must do it before the final exam. After final exam, it won't work. But it's not obligatory. It's totally optional. You can ignore it if you really don't want to give us feedback. You can just ignore it. But I highly encourage you to do that because it's really beneficial to the development of this course. So any questions so far?
For homework 4, should we get the solutions for it before we have the quiz 4? Just so we could know like if we did it right for the quiz on Monday?
You mean the quiz 4?
Yeah. Is it gonna have the questions from homework 4 on it, or similar questions?
Some other questions. It's not. It won't overlap with. Of course, the point we want to observe, I want to examine you might overlap, but we won't give you exact same questions and let you answer. That won't happen.
Yeah.
And after all, the homework solutions sometimes require you to write some program, run some code, right? But quiz, you're not required to do that, right? Because you're not allowed to use computers.
Yeah, can we get the answers though to make sure that we did it correctly and understand the concepts before we quiz them?
The answer of homework
From the
4.
homework. Yeah, even though the quiz questions won't be the exact same as the homework. If we don't know right now if we did the homework correctly, so we might be doing something wrong. So it's helpful to know that before the quiz.
And final.
Yeah, I'm saying before the final. It'd be nice to have the solutions ahead of time.
Yeah, for the final, before the final, we'll release all the answers of the quizzes. We did not plan to release the answers for homeworks because most of you have done a very good job in doing the homeworks. But if you really want to do that, we can release the homework answers. You want to do that?
Again?
Okay. Any other questions? Okay, so let us start the course content. So because in the last lecture, only a few students come in, so we'll spend a bit longer time reviewing what we have discussed the last lecture. But for details, I highly encourage you to watch the video, which has already been shared in the canvas. So in the last lecture, we started with the last topic of this course. It's called classification. Right? So what is classification? So it's very similar to the settings for regression. Right? So for classification, we assume we have several features. Here we assume we have the D features, x1, x2 to xt. We want to use these D features to map the instance they represent to a discrete label. So here y is no longer a continuous value, it is a discrete label. And for simplicity, in our class we mainly talk about binary labels. So the y belongs to either -1 or +1. So it's called a binary classification. And the classification problem actually very common in practice. For example, I want to predict whether somebody will be voted as a president in the next election, right? Well, I want to predict whether my salary will get increased next year, right? A lot of such kind of tasks, and which requires us to develop an automatic algorithm, make the prediction, and then dealing with the regression task, we use linear regression. Right? For dealing with the binary classification task, we introduce the binary classifier. Right? What is binary classifier? What is binary classifier?
So something that assigns one of two labels to an example?
Yeah, that's kind of a rule. The rule how to perform a classification, right? But how do you differentiate linear classifiers from other classifiers? What's the keyword? The keyword is linear, right? So just like linear regression, we introduce a linear function to regress the continuous target variable, right? So for linear classification, we introduce a linear classification function. So we can write it. So here we use a vector x to represent all the D features. So this is the input of our classification function. And then how can we express this classification function. It's very similar to linear regression. First, we introduce an intercept b, and then for each feature, for each of those d features, we introduce a weight. And so for x1, we have a w1. For x2, we have a w2. And we'll continue until xd. So it actually has the same form as linear regression. And then we can simply rewrite it as a vector operations, right? So this is the intercept plus the inner product between the weight vector and feature vector, right? So the weight vector is simply just put all the weights into one vector, right? So then the linear classification function is written as b plus the inner product between the weight vector and the feature vector. So this is our classification function. And sometimes we use even simplified notation because we have an extra scalar outside here. Looks it's kind of troublesome. So it looks like it is not simplified. It is not simple enough. So then we introduce some simplification trick. How do we do that? We just augment the original feature vector by inserting 1. So here I denote the augmented feature vector by what? By adding 1 in front of all the features. So now we have d plus 1 dimensional vector. So it's 1, x1, x2 to xd. So this is d plus 1 dimensional vector because we add a constant feature 1 here. And correspondingly, we can insert b in front of all the weights here. So we get augmented weight vector. So w hat. Right? So the first element in w hat is b, and the remaining elements are w1, w2 to wd. So both augmented feature vectors, augmented weight vectors are now d plus 1 dimension. And then we can rewrite our classification function as an inner product between the augmented feature vector and augmented weight vector. This is a transpose. So we'll use this notation simplification trick to develop our algorithms called perceptron. We'll discuss today. But now let us just be aware. This is a notation simplification trick. Any question at this point? It's just a simple trick here. And then given the linear classification function, how can you perform classification? How can you do the task?
Check the sign.
Yeah, check the sign. It's very simple. It's a rule, right? This is a key difference from the regression, right? If I use linear regression, I just compute this function value. I use function value as our prediction, right? But now, because we want to do the classification, right, what we care is whether it is positive or negative. So actually, we do not necessarily care the absolute value of the classification function. We only care about the sign. So given the classification function, we use this rule we use the following rule to do the classification. That is, we compute the value of the classification function. If it is non-negative, then we'll assign the label of this instance to be a positive 1. Is it clear? I mean, I don't know whether this marker is clear enough because my black marker doesn't work today. If it's not clear, I can use the red one. Any issue? Okay, I'll continue to use this one. So if the classification function value is negative, then assign the label of the instance to be a minus 1. So this is the definition of a linear classifier. We first have a classification function, which is continuous. But then, when we compute the classification function, we check the sign of the value and use the sign to determine the label. This is the definition of linear classification. And then we discussed several important properties about linear classification, mainly from a geometric point of view. So first, we look into the visualization of an equation. The equation says, what if I make the classification function being 0? What does it represent for? Because this is a linear function, right? So actually, this equation is saying this linear function is 0. From our knowledge of stereometry, it actually corresponds to a hyperplane. So you can imagine in the d-dimensional space, this equation defines a separating hyperplane. All the points which stay on this hyperplane satisfy this equation. And this hyperplane actually separates all the points in the d-dimensional space into two parts, one side and the other side. And all the points on one side will be classified as a single label. For example, all the points on this side will be classified as positive examples, and the remaining points which stay on the other side will be classified as negative examples, because their classification function value will be positive on this side, and the classification function value will be always negative on this side. So this hyperplane is also called a classification boundary or decision boundary, because it just will separate all the positive examples from negative examples. And in problem property, by looking into this hyperplane, is that we'll find that the direction of the feature width vector is always proportional, or is always orthogonal to the hyperplane. Of course, it might be orthogonal in the opposite direction. But here, I just choose the arbitrary direction to give you a sense. So just remember, when you talk about a linear classifier, when you draw its decision boundary, then the direction of the width vector is always perpendicular or orthogonal to the hyperplane. And this can be very easily verified by calculating the inner product between this width vector and arbitrary line, which is parallel to this hyperplane. I will show it on the last lecture. You can do it by yourself, right? It's very simple. If we denote this hyperplane by h, then this is our first observation. That is the feature width vector is orthogonal to our hyperplane, the decision boundary h. And the second observation is regarding the distance between the origin and the hyperplane. So in this high-dimensional, in this d-dimensional space, we of course have a origin, right? And then we're curious about the distance between this origin and the hyperplane. And here is the formula. The distance between the origin and the hyperplane is simply the absolute value of the intercept b divided by the norm of the width vector w. And to obtain this conclusion, we need to use the formula. The formula describes the distance between an arbitrary point. The arbitrary point, say, z, to this hyperplane. And here, just give you the formula, and how to derive this formula. You can try to solve it as your practice, or you can watch the lecture video. So for an arbitrary point z that belongs to the d-dimensional space, its distance between z and this our decision boundary is the absolute value of the classification function evaluated as z, so which is w transpose z plus the intercept B, and take absolute value because the distance must be non-negative, and then divide it by the norm of W. And now if we use this formula to compute distance between origin and H, then Z becomes 0, right? And then you multiply W with 0, it's just 0. Then the remaining part in the numerator is just the absolute value of the intercept B, and then divided by the norm of W. This formula is very important because in the future, if you take machine learning class, you must learn some knowledge about like support vector machines. And support vector machines, the motivation to develop support vector machines relies on the distance metric. So, and for traditional convention, because our classification results are not affected by the skew of our classification function, right? Because if we multiply W and B by a large scalar, like by 100, or by a small scalar by 0.1, actually the classification result won't change because the sign does not change. That means given a particular pair of W and B, we'll multiply them both with a constant. It won't change the classification results. So that means for a one linear classifier, it could have an infinite number of equivalent W and B pairs. So for convenience, traditionally we simply restrict the norm of weight vectors to be 1. So we assume our weight vector is simply a unit vector. So in this case, if we restrict or we constrain our weight vector to be a unit vector, then the distance from origin to the hyperplane is simply what? Yeah, simply the absolute value of B, right? This is according to our this is according to our definition, right? So this is in a case that we intentionally constrain the feature weight vector to be a unit vector. Those are two important properties regarding the geometric point of view for linear classifiers. And then we discussed how can we estimate W and B from a set of training instances. So similar to the setting of regression, we might have observed a set of training instances x1, y1, x2, y2 to xn, yn, right? So, but each y1, y2 to yn, they're just binary labels. So then the question becomes, how can we construct an objective function? Right? By optimizing this objective function, we can estimate the optimal W and B. In the last lecture, we discussed how about we directly use the SSE from the linear regression to minimize the distance between the label and the classification function value. This is just a direct copy of the linear regression, but that is problematic. We mentioned that point in the last lecture. The reason is that in classification, we mainly care about whether you misclassified examples or not. We actually do not care whether the classification function value is really close to 1, close to -1. If you use that as your objective, it might have some unfavorable consequences. I will give some examples in the last lecture, and hopefully you have already seen them in a lecture video. And then to develop a more meaningful or more useful objective function to train linear classifiers, we introduce several loss functions. So one of the most influential or most widely used loss is called hinge loss. Hinge loss. So hinge loss is defined as follows: is maximum 0 and 1 minus z. So they can be upper bounded. They can be seen as the upper bound of the oracle loss. So what is oracle loss? The oracle loss is just the number of misclassified examples on your training data. And hinge loss turns out to be an upper bound of the oracle loss. And the hinge loss has a nice property such that it is convex. So its optimization is much easier than other types of loss. So these are important points we discussed in the last lecture. And if you feel unfamiliar with that or feel unclear about that, I suggest you to read the course materials and take a look at the video. We have some detailed description on that. So today we'll start to learn the simplest linear classifier training algorithm called perceptron. So perceptron can be considered as some kind of ancestor or father of neural nets. So although neural nets, deep neural nets, people think it's highly nonlinear, highly non-convex learning machines, but the origin is from perceptron. Perceptron, instead, they only train a linear classifier. So what is perceptron? So let me first list the algorithm steps, and let us first learn how to implement your perceptron, and then we discuss the rationality behind perceptron. So here is the framework for perceptron. So we have n input instances x and n labels y. So in more detail, our training instance could be n pairs. So this is x2, y2, continue, and xn, yn. And here, for simplification, we use the simplified notation. That is, we use augmented weight vector and augmented feature vector to represent our data. So if you still have impression, we just mentioned, right? So we augment the original feature by a constant 1. Right? This is our augmented feature. So but here we are still represented by x1 to xn. And also we augment our original weight vector by inserting the intercept. So here's a b, and then w1, w2 to wd. So we denote this by w hat and x hat. So so let me rewrite the notations to make it more clear. So then the augmented feature vector or input is denoted by x1 hat and y1, x2 hat and y2 continue, and xn hat yn. So when I use hat here, I just emphasize they are augmented by the constant feature 1. So it is d plus 1 dimensional. And also our feature, our parameters is now denoted by w hat because it is augmented with the intercept b and plus the original feature weight vector. So it is also d plus 1 dimensional. And then our classification function now becomes a single inner product. W hat transpose x hat. No question at this point, right? We just use the trick we discussed before. Okay, so here is the perceptron. So I should put perceptron here. Here is the perceptron algorithm. So in the first step, we just initialize W hat to be 0. That means I put all the values in our augmented feature weight vector to be 0. B is 0, W1, W2 to WD in 0. And then we enter into iterations. So we repeatedly do this. We pick up one example and then check the product between the label yi and the classification function value, which is simply the inner product between W hat and X hat. We check whether this product is positive or not. If it is negative, then we update. Then we update our weight vector by adding the input xi, multiplying with the label y. So remember, because yi is binary, yi is either positive 1 or minus 1. So if you update with regard to positive examples, you just add W hat by xi. Otherwise, if you update with a negative example, you actually subtract W with xi by xi, because this is yi times xi hat. However, if this product is non-negative, you do nothing. And here I should add one sentence. If the index of the example is over n, suppose we have n examples, right? We just go back toward the first example. So it's kind of cyclically goes through example in a training set. And you do this repeatedly until there are no updates or maximum number of updates have been finished. That is, we denote it by T, or T updates are finished. This is perception. Of course, we should start. We should set an initial index of the sample to be 0. So in the first step, I get the first example, and then we check the product between yi and the classification function value, which is the inner product between W hat and xi hat. If this product is smaller than 0, then I update W, the weight vector, augmented weight vector, by using this rule. If it is positive, we do nothing. And then I go back to look at next example and check this product again. And if the product is negative, I do the update. I continue to do it until there are no updates. Meaning that for all the training examples, all the product here is non-negative, or the maximum number of updates have been finished. That's the perception algorithm. Any question in understanding this algorithmic steps?
So if I remember it from last time, yi times the classifier, if that's less than 0, then it classified it wrong.
Yeah, exactly.
So then we update if it's wrong.
Yeah, perfect. That's the point I want to discuss right now. So I want to understand the rationality of this updates. What's the meaning of doing this updates? Why we should check this product. So why should we check this product? This product actually is an indicator showing whether your current classifier correctly classified examples or not. And here we can check. If yi times the inner product between the weight vector and the feature vector is non-negative, what does it mean?
It means that the prediction and the actual label were the same. And so it makes it positive, because if they're both negative, then it's positive.
Yeah, correct, right? That actually means that you correctly classify the example xi. You can verify that if xi is positive examples, yi is positive, and this inner product is positive, so they are positive, right? So the classification is right. If y is negative, then y is -1, and to make the whole term to be non-negative, this product must, this inner product must be negative as well, right? That means your classification is right as well. So actually, this product between the true label and the classification function is an indicator showing whether you're doing correctly or not. So now from this condition, we can say perceptron only updates your model parameters, your augmented weight vector, when you misclassify the example. If you correctly classify the examples, that means this product is not negative, then you do nothing. So this is a key idea of perceptron. It's kind of mistake-driven learning algorithm. It updates your model parameters only when you make mistakes.
If we set the W to 0, would the if statement always be false, then the W will not be updated always. If we set W to 0.
Oh, and then you can make a little change, right, to be less than or equal to 0. That's fine. That's totally fine. Any other questions?
So x hat, are all the like x sub 1, x sub 2, are those vectors?
Yeah, they are
So
vectors.
x1 is a vector,
Yes,
d dimensions, but x hat,
it's d plus 1 dimension.
well, isn't x hat though the size of the training data, of the number of observations?
No, the number of observation is n. So you can consider our training instances or training pairs are x1, y1, x2, y2, until xn, yn, right? So for each instance, say xi hat, why should I put hat on that? I just want to emphasize this augmented feature vector. We just put 1 in front of all the features.
Okay, so each of the in x sub 1 is a d plus 1 dimension.
Yes,
vector.
d plus 1 dimension. And also the weight
But
vector.
there are n different pairs of x.
Yes, this is setting. So, and correspondingly, the augmented weight vector is b w1, w2 to wd. So it's also d plus 1 dimensional. And in this way, if we represent data in this way, then our classification function can be simply written as the inner product between w hat and x hat. We do not necessarily to write down that like wx plus b. Because b is absorbed in w, and also some constant 1 is absorbed in x, and then you can simply write it as the inner product between w hat and x hat. It's just a notation and simplification.
Should you normalize the weight vector after each step or once at the end? Or
Once
does it not matter?
once in, you can do the normalization.
Does it matter? I don't.
Doesn't matter. Actually, it doesn't matter. But if you just want to say, I want to conveniently deal with that or to be consistent with our convention, you can do that. But you are not obligated to do that. Any other questions? In understanding this algorithm?
So if the data doesn't fit
Yeah,
then this
very
would-
good point.
this would
That's
go
something I want to-
forever, right?
Yeah, that's something I want to explain later. Yeah. But up to this point, does anyone have questions regarding the whole algorithm steps? It's pretty straightforward. Give you this algorithm, I believe everyone is able to implement your own perceptron. Right. So now that we know this algorithm only updates our model parameters, including the feature weights and intercept, the all that we have, right? When we make mistakes. But does this updates really help improve our classifier? Why we should choose this kind of updates? Why we should add w hat by yi multiplied with xi hat? What's the rationality underlying these updates? This is the second question we want to address. And regarding the convergence issue you mentioned, we'll discuss later. Okay? So we can take a look. We're going to take a look. When we misclassify some example, whether when we update our weight vector according to this way, we're going to improve our classifier. So suppose we have a misclassified some point xi and yi. And then the product yi times between yi and the inner product w hat and xi is negative. And then what happened to our classification function when we perform the updates? We need to check the classification function value. So we update our weight vector by adding yi times xi hat. This is our updated weight vector. Now I want to check, now if I use this updated weight vector to perform a classification, what's the result? How can we check that? We just compute the new classification function value, right? Which is the inner product between this new weight vector and xi hat, right? Any question at this point? So this is an updated weight vector. Suppose right now with w hat, I misclassify this sample, right? So now I follow the rule to update our wi, and I will get updated wi. This is updated. This is updated weight vector. And now I want to use this updated weight vector to perform classification. I want to say whether I have a chance to change. I have a chance to remedy my mistake. And then we need to check the value, the function value. So we can.
Do we need
What?
another y sub I at the beginning of that?
What?
Do we need a y sub I at the beginning of that?
There's a rule.
No, I mean, so that's like the updated weight vector,
Yes.
but don't we need to multiply it by y sub I?
No.
And y sub I times the transpose of the weight vector times x sub I?
This is our updated weight vector, right? So when you calculate the inner product between the updated weight vector and the original feature vector, you get the classification function value for the updated classifier. So imagine you get another weight vector, right? So if I want to use this weight vector to classify xi, how should I do that? I just compute the inner product between this weight vector and xi and check the sign, right? So just do this and then check the sign for that, right? And now, because w hat star is simply this. And now to compute this, we can simply multiply xi into this addition, right? So we have the inner product between w hat, xi hat plus yi times xi hat transpose xi hat. So what does this mean? What does this mean? Xi hat transpose I hat, transpose times I. Just a square norm of Xi hat, right? Some vector transpose times some vector itself. It's just a square norm of the vector itself. Right? So this one is just a square of the Euclidean norm of Wi. So we know that this square norm must be non-negative. This term must be non-negative, right? And then we multiply this non-negative term with yi. So now we can take a look. The classification function value after we update the classifier, the weight. Right? If the misclassified example is positive example, then what will happen?
Value's going to increase.
Yeah, because y is 1. If the original true label of xi is 1, is positive, then we actually increase the classification function value. It's actually helping improve our classifier. Why? Because the reason we misclassify example is because our original classification function value is too small.
It's supposed to be x hat inside of the square norm, right?
Yeah, square norm.
Yeah, so
Oh,
x
yeah,
is
right. Yeah, good. Thanks. The reason we misclassify this positive example is because our classification function value is negative. It's too small. It's below 0. And now, when we update according to the perceptrons rule, we actually increase the function value. If this increment can make our classification function value over 0, we completely correct our mistake. And similarly, if our misclassified example is a negative example, meaning that yi, the ground truth of yi is negative, then what will happen?
Decrease it.
Yeah, it decreases because now yi becomes negative here. So that if we trace back the reason, if yi is negative and we make a mistake, actually it is because our classification function value is too large. It's above 0. So we classify the example to be positive, but it turns out to be negative. And now, to remedy this mistake, we must make our classification function value to be decreased. If it is decreased to be below 0, and then we correct our mistake. We remedy our mistake. So now we can say this simple rule actually is meaningful. It's useful. But it does not guarantee this increment or decrease will guarantee like change the sign. But at least we'll push the classification function value toward the other side. This kind of improvement. Maybe we need to perform multiple updates to completely remedy a mistake. That depends on the algorithm, the practical applications depends on data. So any questions regarding the rationality of perceptron updates? So now we can say why it's called mistake driven. So only when we make mistakes, we update our classifiers to try to improve our classifier to correct mistake. If we do not make mistakes, we just leave it. We do nothing. And someone may ask, like you just asked, what if the convergence properties of this perceptron? So is it possible that when I correct one mistake, I then make another new mistake? Then I will never be able to remove all mistakes. I always make mistakes such that I won't be able to stop these iterations. Of course, if you intentionally set up the maximum number of updates, you can still stop. So here is the result. If the training data is linearly separable, meaning that there is, so suppose this is a positive examples and here is a negative examples, right? if there really exists a linear classifier or decision boundary which can perfectly separate all the positive examples from negative examples, the perceptron guarantees to converge in finite number of updates.
That's gotta be pretty rare though, right?
What?
Is that pretty rare? That the data just fits perfectly like that?
In practice, yes, you're right. It's kind of rare, but it's not impossible. It's not. It's kind of how should I express that? You shouldn't make an assumption that your data is always linearly separable. And there are some ways to deal with such kind of case. But assuming the data is linearly separable is kind of a good starting point to analyze the properties of this algorithm. And based on that, we can develop more advanced techniques to deal with non-linearly separable case.
Is this still, it's still useful though, even if the data is not
Yeah,
linearly
of
separable?
course.
You're not gonna be perfect, but you can get it.
Yeah, of course. Like for example, even I directly use this straightforward implementation of perceptron. Like even I cannot converge if your data is not linearly separable. You just set up the maximum number of iterations. You can imagine. Well, I finally end up with a decision boundary such that I can separate most positive examples from negative examples. Although I have some exceptions, for example here, but the performance of this linear classifier is pretty good. In most cases, it's pretty good, although it's not perfect. But if regarding the theoretical properties, you must make some strong assumptions. Otherwise, you cannot give strong conclusions like convergence properties. So if the data is linear separable, we can guarantee the perceptron algorithm will converge in finite steps, and later we'll introduce the upper bound of this number of updates. And then if the algorithm, the training set is not linearly separable, what will happen? The thing is that it will never converge. It just appears to be perturbating or oscillating. Right? You correct one mistake and make another mistake. You correct one mistake, make another mistake. Just perturbate. But that doesn't mean it's not useful at all.
Yeah. Do we use learning rate?
You are not necessary to use learning rate. You can use that. For example, you can put a learning rate here. It could change, for example, the total number of updates. But even if you do not use learning rate, just put one here, it can guarantee the convergence under the linear separability assumption as well. But in practice, you are free to apply learning rate here.
Does that just make it quicker, theoretically?
Like,
if it just keeps bouncing back and forth, if you're increasing by too much or decreasing by too much?
Yeah, it does affect. It does affect. But there are some theoretical analysis regarding the learning rate. If you plug in the learning rate into the updates, then under the linear separability case, it does affect the total number of updates. Then the upper bound will include one parameters, which is the learning rate. But here, we just ignore learning rate for simplicity. Any other questions? Okay, so and then further a little deeper conclusion regarding the upper bound. That is the maximum updates the perceptron will need to use. To discuss this upper bound, we need to introduce an important concept called margin. So margin is defined on a set of training examples and a linear classifier. So it's kind of a function of two elements. One element is a set of training set or training points, and the other function is a linear classifier. And you must assume this data is linearly separable. Otherwise, it's not meaningful to talk about margin. So let me draw them to make it more clear. Just draw them a set of positive examples and negative examples. So suppose this is our linearly separable training points, right? And we have a linear classifier which shows the decision boundary like this. Now what is margin? The margin is the minimum distance between all the training points and the decision boundary. That's it. So now you can see why it is only meaningful when we say the data points are linearly separable. If it is not linearly separable, how can you calculate the distance?
It would be negative, right? Well,
Oh, it's not negative.
I guess it's not negative because it's a distance, but
Yeah, it is only meaningful when it can well separate the positive example. If it is not well separated positive example or negative examples, then I can place the boundary at any. I can place this hyperplane at any point, right? The distance could be 0. There's no, the principle underlying that. So now from this example, we can say the minimum distance is actually between this positive example and this classification boundary, right? So the margin would be the distance here. And of course, if I change the linear classifier, that means we change the position of classification boundary, the margin changes as well. So if I just rotate this boundary a little bit, now the minimum distance becomes here, right? This is the margin for this new classifier. So the margin is always associated with the training set and a linear classifier. So now let us consider to represent the margin in terms of mathematical formula. So what is margin? The margin is essentially the minimum distance, right? So according from the point 1 to point n, suppose we have n data points, right? According to them, we compute the distance between each data point and the hyperplane. And then pick up the smallest one as the margin. So this is the margin between a data set D and a classifier or a classification boundary H. And what's the distance? Here we use the formula we just mentioned, right? For an arbitrary point, the distance between the point and hyperplane is computed as the absolute value of the classification function evaluated at this point, right? So if you still remember, it is the inner product between the feature weight vector and Sn plus the intercept B. And here I do not use the simplified notation. I do not use augmented trick. I just use the original weight vector and the intercept B, right? And then divided by the norm of weight vector. So this is the definition of margin. And as we mentioned in our convention notification, we just constrain the weight vector to be a unit vector. So when we put this constraint, the margin is simply the absolute value of the function value of the classification function value, right? And further, we can write this absolute value by the product between the label and the classification function value. It's xi. Why? why we can do this. Why this absolute value is simply equal to the product between the label yi and the classification function value.
Same reason from up there, y is negative and multiplied by negative.
Exactly, right? Because our definition of margin assumes that our classifier can correctly classify all the training examples because they can separate all the positive examples from negative examples. That means the product between the yi and the classification function value at the corresponding xi is always non-negative. So this product is always non-negative. So we can use it to replace this absolute value. So why would I like to emphasize the definition of margin? Because margin associated with generalization performance. So actually, many linear classifiers tries to find out a perfect classifier which has the largest margin. So I want to find out a set of optimal weight vector and the intercept by maximize the margin. If you write down the full definition, it's actually a max-min problem. So in the outside, I want to search over all possible WB that maximize the margin. But in the definition of margin, it's the minimum distance between all the points and the classification boundary. So you may feel a little uncomfortable with this max-min optimization problem. But this is a valid optimization problem. It's just not a purely max problem, a purely minimization problem. It's just a max-min problem. And this is actually the objective function for support vector machines. So support vector machines trying to find out classifier which has the largest margin, but also well separate the training data. Do you have any questions?
So is that basically just trying to put it as close to the middle as possible? Like in this case, you get up
Yeah.
pretty close to the.
Yeah, you're right. It just try to push the classification boundary to be as far away from all the training instances as possible. And intuitively, they actually to avoid the high density regions of positive examples, negative examples. So you want the positive examples and negative examples, when they appear again, they are both far away from the region. Otherwise, you can imagine if you stay close to some high density regions, then it is possible that the positive examples can appear on both sides of the hyperplane of the region. Then you have a larger chance to misclassify the example. But this is kind of an intuitive explanation. There is some rigorous.
Does the perceptron incorporate anything with margin?
Yeah, but it's not. But perception, the original perception is not large margin classifier.
It doesn't.
Yeah, I just want to introduce you the margin concept, and also the upper bound of updates is related to margin. So going back to the point we just discussed. So intuitively, we can explain large margin can give you a more robust or better generalization performance, but there are strict, rigorous theoretical guarantees. It links to the computational learning theory. So it turns out that the larger the margin, the tighter the generalization error bound you will have for your linear classifier. That's the motivation for those guys like Vapnik. Those people develop support vector machines. And the later things, all you have heard about, like convex optimization, quadratic optimization, is just the reformulation of this max-min problem, because directly solving this problem is hard. So they use like Lagrangian tricks and those kind of stuff to derive the primal form or dual forms into different problem forms and turn it to be a convex optimization problem. But this is the original definition, and this definition reflects the intuition why they propose this support vector machine. But the details about support vector machine is not our class topic. If you are interested, you can register my class in next semester. We'll discuss in detail the whole formulation of the support vector machines. But here, let us assume we are able to optimize this objective and find out a maximum margin classifier. And this optimal linear classifier has the best margin of gamma star. And what's the usage of gamma star? The gamma star has many good property and many usage to quantify the generalization performance, generation error bound. But here we want to use it to quantify the maximum number of updates used in perceptron. I mean, if the data is linearly separable, as we just mentioned, it will take a finite number of updates to converge. And then the question is, what's the maximum number of updates it will convert? It will perform. So here's the conclusion. Here's the conclusion. So suppose we have a training set, right? Let me draw them again. So suppose this is our origin. Right? For each training input at each feature vector, we can calculate its norm. Right? Its norm actually indicates the length, the distance between the point and the origin. This norm, right? And we just go through all the norms in this training set. We can pick up the largest one. We can denote it by R. So basically, it's the largest distance between the inputs and the origin. This characterizes the span of the training data. Right? And also suppose for this particular training set, we have identified a large margin classifier whose margin is gamma star. Among all the separable linear classifiers, which can classify these data points, this optimal classifier has maximum margin. And then we can bound the maximum number of updates used by perceptron by R over gamma star t squared. So this is the upper bound for rounding perceptron. We start with 0, and we just follow this procedure to update. Whenever we make mistakes, we update our weight vector. And how many updates at most we perform? It turns out to be R over gamma star t squared. So this is one usage of this maximum margin here. So then you can imagine, right? So R actually describes the span of whole data set. So if you draw a circle or a sphere with radius R, it actually contains all of data points, right? And you can imagine inside this data, you just draw many separating hyperplanes. You can find one which has the maximum margin. Means that they are farthest from all the training data points, and the distance is gamma star. And then the maximum number of updates that training perceptron cannot exceed this radius over this distance and t squared. And it's an elegant conclusion, and which is not hard to prove. And if you want to know the detail for the proof, you can check out the course material, at least the proof details. We do not necessary to cover details here, just give you a sense here. And also, one thing you should be aware, perceptron is not large margin classifier. That means you start with 0 and just perform a finite number of updates. You end up with some separable classifier, and this classifier might looks like this. It's different from the optimal large margin classifier. So this is just the upper bound for the number of updates. It does not necessarily mean perceptron will take this number of updates to converge to the optimal large margin classifier. Any questions so far? Okay, I guess we can stop earlier today, and we'll see you next Wednesday. And please do the cosmetic.
Thank you.